The final implementation we're going to look at is the AtomicLong read-write-lock, or RWL. And this implements a subset of this abstract AtomicLong interface using the Java ReentrantReadWriteLock. And it shows how these features work. It shows how things like read locks work, write locks work, and then this concept of reader's writer lock downgrading, which is kind of a funky approach. So let's go ahead and take a look at this. You can see we start out with a field that's just a long, again, it's not volatile. We also go ahead and create ourselves a ReentrantReadWriteLock, which we initialize here as a field. And then we use that ReentrantReadWriteLock to pick out the write lock part and the read lock part. So here's the read lock. We get that with the read lock factor method. Here's the write lock with the write lock factor method. And now we've got these read and write locks, which, as you can see, are locks. And that's what a ReentrantReadWriteLock is. It's a read lock and a write lock and some ways of coordinating things internally. The constructor assigns the initial value to the m value field. Let's take a look at some simple things first. Here's the get method. As you can see, it grabs a read lock, so we want to be able to access m value in a way that won't be corrupted if someone's trying to simultaneously write to it. And when we get the read lock, we know nobody else is writing. There could be other readers. And so we have non-exclusive access, but we have protected access, although it's somewhat pessimistic relative to the stamp lock implementation we looked at. And when we're done, we unlock the lock in the finally block. Now let's take a look at something way more interesting. This is going to be an example of using the reader's writer lock downgrading feature that's available with Java ReentrantReadWriteLock. So the way this is going to work, and you can read more about this feature here at this link, it explains how read-write-lock downgrading works. So we're going to start out here by assigning some value, which is going to be used to essentially store the incremental value of m value, holds the value in a thread-safe manner. And we start out with a write lock held. So if you recall, we had this m write lock field defined up here, which is a write lock. So we're going to assign lock to write lock. We acquire the lock, so now the lock is held, and we may have to block until all the readers or any other writer gets out of the way. Now at this point, we're going to do the downgrading. So with the write lock held, the first thing we do is we increment the value by 1 with the write lock held. We then assign another local variable called read lock to our read lock field, which we initialized up here. And then we go ahead and we acquire the read lock. So at this point, the read lock is held and the write lock is held, and it shouldn't be hard to acquire the read lock because we've already got the write lock. And now what we do is we unlock the write lock. And that means that writers can proceed. And now we've got to, with the read lock held, we can read the value with the read lock held. Now, the thing to note here is because we have the read lock held, we've released writers, but they're not actually going to make any progress until the read lock is removed or released. The writers can't make any progress. So it's perfectly okay at this point to read the value with the read lock held. And then the last thing we do here is we assign the lock variable to the read lock. So now we've got a read lock, and then on the way out, we always unlock the lock in the finally block, and that will turn around and unlock it with the write lock protocol, which in this case is a read lock. So we've downgraded the read lock, and then we return the incremented value. And the basic idea here is to try to make sure that we hold the write lock for a shorter period of time. Although to be honest with you, there really isn't that much of a win here because until the read lock is released, the write lock really can't be acquired anyway. So it's kind of a weird feature, but it's a feature nonetheless. So here are some other examples of using non-downgrading based features. They're way simpler in a lot of ways. So you can see we acquire the write lock, decrement the value, and return the decremented value. And then we go ahead and we also will unlock the lock. And I do the same thing for all the other methods. They're all done in a very simple, straightforward way. So that's the ReentrantReadWriteLock approach. I will go ahead and run this program. I have to warn you, it'll take a little while to run, but I'll start running it. The reason it takes so long to run, of course, is because it's got this ReentrantReadWriteLock going on. The AtomicLong, super fast. The AtomicLong that's implemented with the synchronized blocks, very fast. The AtomicLong that's implemented with the var handle, very fast. The AtomicLong that's implemented with stamp lock, very fast. The AtomicLong that's implemented with reader's writer lock is really, really, really slow. So I'll let it run. Just be aware that in practice, it's pretty much the case that you're better off sticking with these other implementations of synchronizers rather than ever using ReentrantReadWriteLock. They probably should honestly have deprecated this feature altogether because it really doesn't provide any value in Java, but it's there primarily for backwards compatibility purposes. The only thing I'll say in some defense of reentrant read-write lock, and it's very hollow praise, is unlike stamp lock, it's reentrant. So if you are absolutely desperate and you have the right set of situations, it might not be the most horrible thing in the world. However, as you'll see when we look at the performance results here that'll come out in a moment or so, it's orders of magnitude slower than all the other approaches, even the approaches that do not differentiate between reads and writes. And if you recall, this original program that we're running here was set up to have a whole bunch of readers. We had, I think it was 20 readers going simultaneously and some smaller number of writers. So this is a very reader-dominant implementation. And so you'd expect that if you had an effective reader's writer lock, you'd see a win. And so here's what the results look like for this particular execution. You can see for this particular execution, the stamp lock was the best. It doesn't always work the best, but sometimes it works the best. AtomicLong did very well. The one that used the synchronized blocks worked very well. The one that used the var handle was a little slower for reasons I'm not entirely sure. Maybe it's the wrapper overhead of getting access to the compare and swap operations using a var handle. But all of those methods work way better than the dog slow reader's writer lock, which is just abysmal. So that's the end of that discussion. I just wanted you to understand these different approaches, and now you have a good understanding of how to use the different forms of reader's writer locks and how they compare and contrast with other ways of doing synchronization in Java.